3, 4, we talk about real zeros of polynomials, how to find the zeros of polynomials. Having synthetic division does make evaluating a little bit quicker, but what are the possible roots? There's just so many that are possible. Well, there are a couple of methods here that rules here that help out. There's the rational roots theorem. There's Descartes' rule of signs. There's upper and lower bounds. They really help you concentrate on where to look for roots. The rational roots theorem says this: if p equals a(n)x to the n plus a(n minus 1x to the n minus 1 all the way down to a1x plus a0, then every rational root of p is of the form p over q, where p and q are integers in lowest terms, and p divides into the last term, a0, and q divides into the leading term, an. So the rational roots theorem says that this polynomial has a root of the form divisor of a0 divided by divisor of an. Every rational root is of that form. Now here's a proof. It goes like this, and you'll find it in the book. If p of p over q is 0, then you plug it in, a of p over q to the n plus an minus 1 over times p minus q to the n minus 1 all the way down to a0 is 0. If you multiply by q to the nth, you get an p to the n plus an minus 1 p to the n minus 1 q plus a bunch more terms all the way up to a0 q to the n. Now, if we move every term except the first over, if we move the leading term to the other side, and you divide a q out of every p out of every other term, you get p times stuff equals minus a0 q to the n. Now, I should have said that we're assuming here that all the coefficients and so on are whole numbers. So we're talking, this is a whole number equation. And p divides the left side, because here it is, but it has to divide the right side. But if p and q have no common factors, then p has to divide a0. And also, if we going from here, we proceed to transpose all the other terms and pull out a q, we'll get that q has to divide this right side, and therefore it has to divide this left side, and it doesn't divide p, so it has to divide an. So p must divide a0, the last coefficient, and q must divide an, the leading coefficient. So for example, what are all the possible rational roots of x cubed plus 4x squared minus 3x minus 18? It has to be of the form, any rational root must be of the form of divisor of negative 18 divided by a divisor of 1. Well, there are only so many divisors of 18, and there are only two divisors of 1. So it's plus or minus 1, or plus or minus 2, or plus or minus 3, or plus or minus 6, or plus or minus 9, or plus or minus 18, all over plus or minus 1. Well, or in other words, it's just plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. That's 12 possibilities. It's, a fair number, but it's less than infinity. And if you check all 12 possibilities, you'll find that the roots are 2 and negative 3. Those work, the others don't. Those are all the possible rational roots. Let's find the rational roots and factorize x to the fourth minus 5x squared plus 4. Well, okay, a rational root must be the form of divisor of this last term 4, divided by this leading coefficient 1. Divisor of 4 over divisor of 1. That's plus or minus 2, or plus or minus 3, or plus or minus 4 over plus or minus 1. Here they are: 1 minus 1, 2 minus 2, 4 minus 4. 6 possibilities. Check them all. Well, all right, so we'll divide 1 into this. 1, 0, negative 5, 0, 4. 1, 0, negative 5, 0, 4. And try to check out 1. Down comes a 1, times 1 is 1, plus 0 is 1, times 1 is 1, plus negative 5 is negative 4, times 1 is negative 4, plus 0 is negative 4, times 1 is negative 4 is 0. P of 1 is 0. And that means that P of x is x minus 1 times the polynomial this encodes, x cubed plus x squared minus 4x plus 4. All right. P of x is x minus 1 times these. Now, what happened here is that now we have to find all the roots. We only have to find roots of a third degree polynomial. Before it was a fourth degree polynomial. We've done what's called extracting a root. Now all the roots of the polynomial are in here, so it's a simpler problem. Okay, so well, okay, the irrational roots of this are plus or minus 4, or plus or minus 1, or plus or minus 2. So try -1 on this, mind you, since it's a simpler problem that way. -1 is a root of 1, 1, -4, -4 here. Okay, down comes a 1 times -1 is a -1, plus 1 is a 0, times -1 is a 0, plus -4 is a -4, times -1 is a 4, plus -4 is a 0. Ah, so P at -1 equals 0. Well, we've extracted another root. So our whole polynomial will be x minus 1 times x plus 1 to make this 0. And then we're left with x squared minus 4 from here. Okay, now this is easy enough to factor. X squared minus 4 is a difference x squared minus 2 squared, and a difference of squares is difference times sum, x minus 2 times x plus 2. So P of x is x minus 1 times x plus 1 times x minus 2 times x plus 2. That's the complete factorization of the polynomial. And its roots are when this is 0, or this is 0, or this is 0, or this is 0. This is 0 when x is 1. This is 0 when x is -1. This is 0 when x is 2. This is 0 when x is -2. And those are all 4 roots of this original polynomial. Now there's some tricks about the Descartes rule of signs and the upper and lower bounds theorem give you some hints about where to go if you use synthetic division, where to look for roots. If there are how many positive roots, how many negative roots, what's the biggest possible root, what's the smallest possible root. If you write a polynomial in descending powers of x, then the variation of sign is when adjacent coefficients have opposite sign. Now, if that's so, and if k has k variations of sign, then it has k minus some even number of positive roots. And if you look at p at -1, which basically flip the sign of every odd power, and if it has j variations of sign, then p of x has j minus an even number of negative roots. For example, let's consider x cubed minus x squared minus x minus 3. If you look at it, it has one variation of sign from here to here. That's it. These are all the same sign. It has one variation of sign, so it has one and only one positive root. If you look at p at -x, then this flips, x cubed flips, the x flips. We have -x cubed minus x squared plus x minus 3. This is 1, 2 variations of sign. And so p of x has 2 or 0 negative roots. 1 positive root, 2 or 0 negative roots. Here we have minus x to the 5th plus 4x cubed minus x squared plus 6x. How many possible positive roots and how many possible negative roots? We have look at p of x. We have 1, 2, 3 variations of sign. And p of -x is x to the 5th minus 4x squared minus x squared minus 6x. That's just one variation in sign. So p has 3 or 1 positive roots, and has only 1 negative root. So this gives you a hint as to how many roots to look for. There's something also called the upper and lower bounds theorem, which tells you how big the roots could be. If you divide p of x by x minus b, where b is positive, and the quotient remainder row has no negative entry, then all the real roots of p are less than b. And if you divide p of x by x minus a, where a is negative, and the quotient remainder alternates between non-negative and non-positive, then all the real roots of p of x are greater than a. So for example, let's try x to the 4th minus 3x squared plus 2x minus 5. And if we divide, say, synthetically divide by 2, after a bunch of work, we're left with this in the last row, unless these are all non-negative, so all the real roots are less than 2. Here we'd synthetically divide by -3, and after some work, 1, -3, 6, -16, 43. This alternates between plus and minus. So all real roots are at least -3. So all the real roots are between -3 and 2, as shown by this and this. So for example, let's try the rational roots and factorize 4x cubed plus 8x squared minus 11x minus 15. Now, all right. There's one variation in sign here, so there's one positive root. P of negative x, you flip this and this, minus 4x squared, x cubed plus 8x squared plus 11x minus 15. There's two variations of signs. So there are 2 or 0 negative roots. 1 positive roots, 2 or no negative roots. That's a hint. It helps. Now, as for the rational roots, we take a divisor of 15 over divisor of 4. Here are the divisors of 15, 1, 3, 5, 15, plus or minus. Divisor of 4, 1, 2, 4, plus or minus. So this ratio comes out to these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities. No, 24 possibilities. All right, let's try some. Let's try, for example, let's try 5. 4, 8, negative 11, 15 is the polynomial. 4 times 5 is 20, plus 8 is 28, times 5 is 140, plus negative 11 is 129, times 5 is 645, plus negative 15 is 630. These are all positive, so all the roots are less than 5. Try negative 3. Down comes 4, times 3 is negative 12, plus 8 is negative 4, times negative 3 is 12, plus negative 11 is 1, times negative 3 is negative 3, plus negative 15 is negative 18, plus, minus, and alternates. So all the roots are greater than negative 3. So we now know that the roots are between negative 3 and 5. There's only 1 positive roots, and there are 2 or there are negative roots. Again, time savers, handy hints. Well, all right, let's try negative 5 halves. I mean, look among these things for 5. We can throw out 15. We can throw out 15 halves. Let's try 5 halves. We'll say negative 5 halves. All right. Down comes 4 times negative 5 halves is negative 10, plus 8 is negative 2, times negative 5 halves is 5, plus negative 11 is negative 6, times negative 5 halves is 15, plus negative 15. Aha, is 0. So P at negative 5 halves is 0. And reading off the quotient remainder polynomial here, get that P of x is x plus 5 halves times 4x squared minus 2x minus 6. Now I can make things a little easier by pulling out a factor of 2 from here, and times 2 is 2x plus 5. Remaining here is 2x squared plus x minus 3. So if negative 5 halves is a root, and this contains the other roots. So let's try 2x squared minus x minus 3 here. Let's try against, and since we have a negative root, there has to be, at least it has to be another one, because there's 2 or 0 negative roots. Let's try negative 1. 2, negative 1, negative 3. After the appropriate adding and subtracting, we get a 0. P at negative 1 is 0. So P of x is this 2x plus 5. Factor out an x plus 1 to accommodate for this, and times 2x minus 3 from here. Now, if this is the full factorization of P of x, then zeros are when this is 0 at negative 5 halves, or this is 0 at negative 1, or when this is 0. 2x minus 3 is 0, means 2x is 3, and x is 3 halves. So we have all 3 roots, negative 5 halves, or negative 1 or 3 halves, and P of x is like here, 2x plus 5 times x plus 1 times 2x minus 3, and these are the solutions. Here we do the same thing, find the rational roots and the factorization of x to the 5th plus 3x to the 4th minus 9x squared minus 31x squared plus 36. Before I go on, I should warn you that as neat as it looks here on this page, the truth is, of course, is that I had another page where I did a lot of scribbling as I tried and rejected various roots which didn't work out. My advice to you is to do the same thing. Part of the part of how math works is scratch paper. We proceed. And neat writing on the main paper. 90% of my students' errors are clerical, so be advised. All right, so here, looking at this, there's 1, 2 variations in sign. So there's 2 or 0 positive roots. If you plug in negative x, then the 5th power, the 3rd power cancel, flip, so you get this, and you get 1, 2, 3 variations in sign. There's 3 or 1 negative roots. So, okay, these are handy hints. Rational roots of this polynomial are divisors of 36 divided by divisors of 1. It comes out to these possibilities. 18 possibilities. All right, let's try negative 6. And after synthetic division, we get this here, 1, -3, 9, -85, 5, 10, -30, 24. It's an alternate, so any root is bigger than -6. Try 4, we get 1. After alternation, you get 1, 7, 19, 45, 180, 756, all positive. So any roots are less than 4. So there's 2 or 0 positive roots, 3 or 1 negative roots, and they're all between -6 and 4. That's a fair number of helpful hints. And here are all the possible rational roots. Okay. Well, I mean, 4 doesn't work for a positive. Let's try 3. Okay. Down comes 1 times 3 is 3 plus 3 is 6 times 3 is 18 plus -9 is 9 times 3 is 27 plus -31 is -4 times 3 is -12 plus 0 is -12 times 3 is -36 plus 36 is 0. Yay. So P of 3 is 0. We found a root. And what's more, this 4th degree polynomial has all the other roots. X plus x to the 4th plus 6x cubed plus 9x squared minus 4x minus 12. That times x minus 3 is P of x. So we work with this. See what the roots are of this. Put it here. Let's try 1. Well, 0, bang, P of 1 is 0. Good. And so with having us extracted x minus 1 from this, we have the P equals x minus 3 times x minus 1 times x squared cubed plus 7x squared plus 16x plus 12. Now we know that there are only 2 or 0 positive roots, and we've used up both of them. So all the other roots are negative, and they are roots of this here, x cubed plus 7x squared plus 16x plus 12. Put that in here. All right. Now we could try various things. It has to be, the roots has to be, negative roots have to be bigger than -6. Off paper, off screen and on paper, I tried -4. Didn't work. Let's try -3. Down comes 1 times -3 is -3 plus 7 is 4 times -3 is -12 plus 16 is 4 times -3 is -12 plus 12 is 0. Yes, P at 3 is 0. So P of x is x minus 3 times x minus 1 times x plus 3 to accommodate this times this 1x squared plus 4x plus 4, like that. Now this is a quadratic. X squared plus 4x plus 4. It's fairly routine to factor it into x plus 2 times x plus 2. So we're done. P of x is x minus 3 times x minus 1 times x plus 3 times x plus 2 squared. So the roots of P of x are when this is 0 at 3, or when this is 0 at 1, or when this is 0 at -3, or when this is 0 at -2, but because of a square, this is a double root, so to speak, twice. So those are all the roots of that polynomial. All right.